today. We talked about welding is a process in which two materials are joined either by alone heat or heat plus pressure application. And based on that, we also talked about the advantages of welding over riveted connections or other kind of things. And then there is also like welding can also be used as an alternate for the casting or forging. And then there are little bit disadvantages of welding. The disadvantages are we need a skilled labor. Requires skilled labor. Inspection specialized tools and others. And then we talked about different types of welding process, like with only heat, and where only heat is there, which involves two categories, as we said earlier, where it is heat alone. This has heat plus pressure. In the heat alone, we have thermit, gas welding, and electrical arc. Whereas in this, we have forged welding and electric resistance wearing. These are the kind of things we have seen. After that, we have started looking at the joints. Mostly in this chapter we'll focus on the aspects of as a joint rather than the casting or forging process. So then we looked upon different types of joints. First one is a butt welding, and the second one is fillet welding, or butt joint and a fillet joint. Or you can also call it a slab joint. In the butt, they both lie in the same plane, the adjoining place, almost on the same plane, and they are attached to each other. Whereas in fillet, the two plates which are about to be joined are overlapped on one another. So this is the thing. So again, fillet is further divided into two types: transverse fillet and a parallel fillet. In the transverse fillet, the weld direction is perpendicular to the force application, whereas in this direction is parallel to load direction. Today, it is our job to use this thing to kind of start designing the stuff. So how the a welded joint would behave. So in order to do that, we need to understand the strength of the both the butt weld as well as the strength of the fillet weld. So I would first, what I will do is, generally I'll give you uh, the the design things, and later I'll explain that why we are using this. We'll come with little parts. So first one, strength of the butt weld. Okay, I don't have a picture, but I'll quickly draw it for you. It should not be a problem. In the butt weld, let's say this is the weld bead. So even though it is like that, when we are, so this, when I look from the top, we have a weld bead which is in this form, but for calculations we only consider the weld bead to be as only V. We don't consider this top portion. That top portion is an extra reinforcement, so this we will consider for calculations. This enlarged view is here. So, and if you look at it, this is the length of the weld, and this is the height of the plate. Let's assume that both the plates are of equal thickness. So the height of this would also be h. So since these things are subjected to load, tensile load P, by, let's say, sigma T we define as the tensile stress of the weld, then the resisting cross section is the critical cross section, which would be this cross section which is passing through the center. So we know its height is h and its length is L, so it is the net cross section. So sigma P is equals to sigma T H L, where sigma T is tensile stress in the weld, and H is the throat thickness of the butt weld. L is the length of the weld. This is what generally the total load carrying capacity of a butt weld depends upon the tensile strength. So if you replace tensile stress by strength, it will give you the load carrying capacity of a tensile of a butt weld. Now, in most of the design codes, such as they restrict, depending upon the quality of weld, they give you the efficiency of the weld joint. So the codal provisions such as so they introduce an efficiency factor or efficiency parameter because generally pressure vessels are requires higher safety because like boilers in chemical industries or any other pressure vessels, when they explode, it generally creates a lot of catastrophe and human loss. So in that reason, these pressure vessel codes generally has suggested an efficiency parameter or efficiency factor, and hence our total load has to be corrected or reduced with this efficiency factor is equals to sigma T HL for the butt weld. So this is how a butt weld has to be designed. Let's have a look at an example. Consider a gas tank of a cylindrical shell of 2.5 meters dia. It is enclosed by hemispherical shells by means of butt weld. As shown in figure below. the thickness of the hemispherical cover is 12 mm. Find the allowable internal pressure to which the tank may be subjected. If the permissible tensile stress in the weld is 85 Newton per mm square. Assume efficiency of the weld joint as 0.85. So for this, let us see the tank, how it is there. This is the tank cylindrical shell over which this hemispherical and this hemispherical are joined. So this is cylindrical shell. These two are hemispherical shell, and these two are so what we know here is the capital D is 2.5 meters. The thickness of these plates is 12 mm. The sigma T for the butt weld is 85 Newton per mm square, and the efficiency is 0.85. So based on this, first what we need to calculate is the total load or the tensile load taken by these plates, because under the pressure this cap will be pushed to this side and this will be pushed on this side. So that is the amount of things has to be resisted by the load transfer P that will happen between these two things. So let us calculate the tensile force in the plates. So for that, since it is cylindrical in nature, the circumference or the perimeter of the weld is equals to pi times d, that is equals to 3.14 times 2.5 meters. That comes out to be 7.853 meters. Now the length of the weld, right? So now according to our formula, P is equals to sigma T into T into L into things. So the where T is the, or you can, if you don't like, if as per the, it is H is there, our H is T, so I will write it as from the previous formula HL neta, where throat thickness is equals to thickness of the plate. So I can write it as sigma T TL. This is throat thickness of butt. Sorry, this. So we have to write our tau max is equals to P sin theta cos theta plus sin theta by HL at theta is equals to 67.5 degrees. So we can write our tau max on simplification as 1.21 P by HL, or P, yes, in this case is given by 0.8284 HL tau max. For unit length, that is L is equals to 1, we can write it as PS is equals to 0.8284 H tau max. Now if we take the ratio, this is for the transverse. So PS transverse divided by PS parallel is 0.8284 H tau max divided by 0.707 H tau max. That comes out to be 1.17. That is transverse weld 17% more than parallel fillet weld. But in principle, people ignore this thing. In principle, people ignore this stuff, and this makes the calculation simpler. Hence, same formulas can also be used for transverse case. Okay, so with this as the now we know that the same formulas which were simpler in the parallel case can be applied even for this case. The next one what we will go and study is the case of an unsymmetrically loaded weld joint. So if you want to, in this, I will give you a typical example. Like if you have an angle section or a channel section or T joint or something like that, these I mean, T sections and angle sections are generally unsymmetric in nature. So that will result in kind of an unsymmetrical loading. And if by the addition of this weld, our purpose is to kind of retain the same center of gravity. So without changing the center of gravity. So that is what has to be, will be targeted when we are designing an unsymmetrical weld joint. I will show you an example. By the weld 1 and 2 respectively. Which is 1? You have seen this is the 1 and this is the second part of it. So our total load P is resisted by P1 and P2. But what is P1 according to the equations we just solved? It doesn't matter. In this case, it's a parallel weld. So we can directly take, even though it may be transverse, we discussed that we can directly make use of the same equations. Point H0 is H, the length is L1 times the shear stress or the shear strength. Similarly, P2 is 0.707 H L2 tau, where this is L2 and that is the L1. So by this, we have satisfied the force balance. So this force is compensated by force P1 and P2. But in order to maintain the center of gravity same, the moment about the center of gravity has to be zero. Otherwise, it would not make sure our center of gravity is unchanged. That means we have to satisfy an additional criteria that this forces which creates a moment, because these are two unequal forces, has some arm length from the center of gravity. So this moment and this moment has to be the same. So that means P1 Y1 is equals to P2 Y2 to retain same CG. So if I express these things, it boils down to this implies 0.707 H tau is common for both the things. So that implies L1 Y1 is equals to L2 Y2. Further, the total length of the weld is given by L is equals to L1 plus L2. So these are the three equations this has to satisfy. That is the first, third one. So if it satisfies all these three, then we are making sure that when you have an unsymmetric cross section, then in those cases, the top portion and bottom portion will also be unsymmetrical in nature and as per the proportions dictated by these equations. For that, let us solve an example and clearly understand these things. The example is same as this one, so we'll again recopy the same figure, but let us note down the problem first. Consider an ISA 200 by 100 by 10 angle to a steel plate by means of fillet welds as shown below. The angle is subjected to a static force of 150 kilonewton and permissible shear stress of the weld is 70 Newton per mm square. And we need to determine the length of the to 108.81 mm and L2 is 194. So these are the two different things that will be applied at the bottom. This is at bottom and this is at top. So this will make sure the center of gravity G is unchanged. So this is how you do axially loaded unsymmetrical welded joint. The next one we will talk about is the eccentric loads in the plane of weld. So for this case, we will show how it generally looks like. So when you're designing some gantry girders and other things, sometimes you will get these kind of things where your eccentricity is only in the plane of the weld. This generally comes for the brackets. So I will show that. So if you look at, this is the plane and this is the load in that plane acting in the same plane, but it is acting, this load is acting at a distance of E or at an eccentricity of E from the center of gravity. Okay, so this is the reason it is called eccentric load in the plane of weld. So we can convert this guy as this load is acting at the center of gravity and also this would generate a moment. So this that is equivalent to P times E also acting at the center of gravity. So this again further considered as a superposition, that is, this is the stresses coming from only axial load and the stresses coming from the moment, and the stresses coming from this is called primary and the stresses coming from the moments are called secondary in nature. So this will give primary shear stress and this will give secondary shear stress. The net shear stress is the resultant of both the things. So this is how we are going to solve this problem of the things. So this will give primary. So let us note down. This will give primary shear stress. This is secondary. And then we need to find out which is both will give us resultant. So it is not simple addition in terms of stresses. In stresses, we need to a kind of square root mean has to be taken to get the resultant shear stress of the magnitudes. So for that, let me show this part again in terms of stress distributions. So the primary shear stress is obtained by this load P acting at the things, and which is tau 1, and tau 2 is obtained by the moment acting because of the eccentricity, and then the resultant tau is the kind of. So let us calculate these things. So tau 1 is simply given as P by A. It is not the resisting area, whereas tau 2 is given as, because it is bending, it is given as mr by J, where R is the uh, distance measured from G, and J is the polar moment of inertia. M is equals to P times E. This is simpler. And further, when you are actually solving it, we don't really solve for all R. We are only resulted in the critical sections. So where does tau 2 will be highest? The tau 2 will be highest when R is highest. So R is chosen such that it will give us, so instead of R, we'll choose R max into the consideration. Further, now in this case, if you look at it, if you have a weld bead at the top and the bottom, which is representing in this case, our J is equals to Ixx plus Iyy is the thing, and our A in this is the area of the total weld. Net resultant thing is H into L. So, or in this case, it is the thickness of the weld. So, or the throat thickness H times L. So anyway, this is the thing. So let us consider this as H this throat thickness as h, and this is our given length L in this given stuff. So we can easily write our Ixx as since this is like a rectangular, um, we will write it first for this part alone, and then we'll make shift it to the center. So cube by 12 is the Ixx, and Iyy is HL cube by 12, because H is much less than L, so Ixx is much less than Iyy. So in these cases, we approximate this guy as close to Iyy. So based on these things, we can write it as it is HL cube by 12. So J is approximated as HL cube by 12 about, let's say, G1, which is about the center of this. Let's say this is G1, about the center. But we don't want about this center. We want about the entire assembly center of gravity with this G. So for that you need to use parallel axis theorem. The total J about G is JG1 plus A R square, or so in this case is the distance between G and G1. So that we can write it as, you can write this one as A L square by 12, because A is H into L. So on simplification, we can write it as A times L square by 12 plus R1 square is JG. So this is for the one given stuff, but like that, in this case you have second thing on the other side. Because of symmetry, this R1 G1 distance is same as G0, so you can keep on adding it. So total J is nothing but J1 plus J2 plus so on. In this case, J1 and J2, this is for the 1. So J in this case is 2 times A L square 12 plus R1 square is the J. So now if you know J, we already know the maximum distance R. We know M, which is P times E. We know B, we know A. So we can calculate the primary share as well as the secondary share, and then take the resultant share, and that will finish the problem. So let us see that thing using an example. So example, a welded connection as shown below is subjected to an eccentric force of 7.5 kilonewton, determine the size of weld if the permissible shear stress for the weld is 100 Newton per mm square. So this is the problem. So in this case, our P is equals to 7.5 kilonewtons. E is, if you can measure it, you can see that E is equals to 25 in this place, which is half, and from here it is 100, so it is 50 by 2 plus 100, 125 mm in this case. Next, our tau is equals to 100 Newton per mm square. So first one is primary shear. Primary shear tau 1 is equals to P by A, that is equals to 7,500 divided by 100 is the area, because it is 50 and 50, and the throat thickness would be the T. So this will give you 75 by T Newton per mm square. Now this is your primary shear. Now second comes is secondary shear. In our case, M is equals to P dot E. This is 7,500 into 125, which will give 937,500 Newton mm. And so in this case, you can see this is 25, this is 25, and this distance is 50 as we shown. The farthest distance is this one, so we will take that one into the consideration. And so for this, we can note down our R1, this center to that center distance, R1 is 25 mm, and our maximum R max is equals to 25 square plus 25 square, that is equals 35.36 mm. This is your R or R max, whatever you would like to call. Then our J is equals to A times L square by 12 plus R1 square. For this part, this is for the J1, let's call it as J1, and this is J2, and this is given by 50 is the length, T is the throat thickness, or H is the throat thickness, into L square, which would be 50 square by 12 plus 35.36 whole square. That comes out to be 0.4167 times T. So since it is symmetry, as I said, J is equals to J1 plus J2, or you can write it as 2 times J1 because J1 is equals to J2 due to symmetry. That is equals to 8334 times T mm4. So now tau 2 is obtained as m into r max divided by j, that is equals to 937500 times r max comes out to be 35.36. Sorry, this is R1. R1 is 25 per S. So J is 83334 times T. So it happens to be 397.8 T Newton per mm square. So if I take resultant of tau 1, tau 2, then the resultant share is happens to be 454 by T Newton per mm square. Now, but we know that tau permissible, tau has to be less than tau permissible or less than or equals to. So if we equate, this one is 100. So 454 divided by T is equals to 100. That implies T is equals to 4.54 or about 5 mm weld is required. So this is the size of the weld that is required so that this structure can take up this load with the given eccentricity. So this is for the case for the eccentric load in the plane of it. Similarly, we can also solve for the problem with the things with the bending. So for the bending, the resultant shears are a little bit different because you get both axial as well as the shear stress. So you need to calculate both the things and also have to find out the axial stress, the resultant shear stress. So the next thing we will do is welding joint subjected to bending moment. So if you look at it, you have a weld on the top and on the bottom. So that is results in this kind of a loading. So because this is the kind of the load is applied at a distance E on this bracket, so this will cause an eccentric loading P into E. So that division can be again calculated based on the previous resultant superposition method into the following manner. So this will end the moment coming from P into E. And again, these net loading is divided into a problem with only P applied and a problem with a M applied. So as the kind of a shear stress, and MB will give us axial loading in this case. And the axial loading, from the axial loading, we have to find out the net resultant shear, and that formulas we will give it now. So the primary shear, this is primary, this is primary, this is secondary. So first one, primary is given by tau 1 is equals to P divided by A, where A is the throat area, and in the secondary, bending will lead into axial stresses. So sigma B is given as MB Y by I. Y is the farthest fiber, I is the moment of inertia about the bending axis. So this is the case. So for our things, let's say Ixx for such a scenario where this as the cross section, then we can show that for this cross section of welding, Ixx is Vt cube by 12 plus Bt into T by 2 whole square. This is the correction for the parallax theorem, or since this is very small, it can be ignored, or it can be written as Bt d square by 4. And since you have on both the sides, this is for one side, for the one, similarly Ixx is equals to Ixx on the one side plus Ixx on the second side. That will be 2Bt d square by 4, or T into Bd square by 2. So this is the first side, this is the first side, and this is the second side. So with this, we get our this Ixx will be used here, and Y is the farthest distance. In this case, your Y is this distance, so Y is equals to d by 2. So the farthest distance in this case. MB d by 2 divided by T Bd square by 2. So sigma B is equals to MB by T B D is the sigma, but this is only the axial stresses. This axial stress is related to shear stress in a manner that our resultant shear stress, in this case tau is equals tau 2 square, so that would be tau 1 square plus sigma B by 2 whole square. The thing, this has to be less than tau permissible. So this is the design criteria that has to be applied. I think this is getting late. So what we'll do is I will take an example of the bending case in the next class, and there is one more is when the sections are subjected to torsion. That case we need to do these two cases, and then the design of the weld under fatigue loading. So we need to consider the endurance into the consideration, and there are certain standards that give the permissible stresses for different types of weld. There are two such scenarios when we have the weld which is same or more than the base plates, or the scenario when we have strength of the weld is less than the base plate. So these things we will cover in the next class, which should be next Wednesday at 2 o'clock.